In the previous video, I showed you that when work is done on an object in opposition to a conservative force, that work can be stored as potential energy, and then that potential energy can be converted back into kinetic energy as the object returns to its initial position. We can say that in a situation where only conservative forces are acting, the combination of kinetic energy and potential energy is a constant. The combination of kinetic and potential energy is what's known as the mechanical energy. Okay? So the mechanical energy is, by definition, the sum of kinetic energy and potential energy. So this statement here, which says that kinetic energy plus potential energy equals constant when only conservative force is acting, this is often known as conservation of mechanical energy. There are other ways of expressing conservation of mechanical energy. Here we have said that if only conservative forces act, then the combination of kinetic and potential energy is a constant. Another way of saying that is that if we have a process where only conservative forces act, then during that process, the change in the combination of kinetic and potential energy is zero. If only conservative forces act, we can then say that the change in the combination of kinetic and potential energy would be equal to zero. This statement here would be another way of expressing conservation of mechanical energy. For a third way of saying this, if the change in the combination of kinetic and potential energy is zero, then it also must be true that if only conservative forces act, then the change in kinetic energy plus the change in potential energy for a given process would be zero. So now we have a third expression of conservation of mechanical energy. In order to actually solve problems using conservation of mechanical energy, we need to be able to calculate potential energies in scenarios where conservative forces are acting. I'm going to start by showing you how to calculate gravitational potential energy. Then, in the next couple of videos, we will do example problems involving gravitational potential energy, and then later on, we will get to other forms of potential energy. Here's how we calculate the gravitational potential energy. We start by introducing what we call a zero level. The zero level is a horizontal level which extends infinitely in all directions. Let's say we have a mass right here, which is at the zero level. That mass would then have a gravitational potential energy equal to zero. Any other mass at the same height would then also have a gravitational potential energy of zero. If we have a mass m at a height h above the zero level, then its gravitational potential energy is equal to the mass of the object times little g, the free fall acceleration, multiplied by the height of the object above the zero level. On the other hand, let's say we have an object of mass m, except that it is below the zero level. Let's call this distance something else. Let's say capital H. What would be the gravitational potential energy of this mass over here, a distance capital H below the zero level? The gravitational potential energy of that object would be equal to minus the mass times the free fall acceleration multiplied by that vertical distance h between the mass and the zero level. Let's do a quick example. Let's say that I put my zero level here. And let's say that up here I have a 4 kilogram mass. And let's say that it is at a height 7 meters above the zero level. What would be the gravitational potential energy of that object? So we'll just start with the formula. Gravitational potential energy equals mgh. So our mass is 4 kilograms. Little g, as usual, 9.8 meters per second squared. Height 7 meters. I get 274. Now let's look at the unit. We have kilograms, meters squared over second squared. And notice that this is joule. So the gravitational potential energy of this object relative to the zero level would be 274 joules. And notice that we have the same unit for gravitational potential energy that we do for kinetic energy and work, as we would expect. In the next couple of videos, we're going to be doing a couple of example problems using the gravitational potential energy.